So we're going to start with a spring problem here. So in this problem, this spring equation, what I have here, I have a spring constant and then a delta x, which is a displacement. So what that means is that, say for example, I have a spring, it's sitting flat on a surface, okay? If I want to stretch that spring a little bit further, so I want to stretch it out by some delta x, okay, it would change the amount of force in that spring, okay? Now say I want to compress that spring, so I want to push it back the other direction, okay, and I want to compress it more, say it's against a wall, and then that spring would be a little bit more smushed. This would also be a delta x. So I can stretch or I can compress my spring. The important thing to note is that when I stretch or compress my spring force, Fs, is always going to be trying to point back to that equilibrium position, right? So the energy that I put into that spring by smushing it or stretching it is going to create a force that wants to push it back to its equilibrium point at rest. Okay, so just assume that the starting spring is at rest. Okay, so delta x can be in the x or the y direction. So if I have a hanging spring, that delta x could also be vertical. We'll see that in this problem here. So conceptually, we covered this. So let's go ahead and get started. Okay. So a typical way to measure a spring constant K is to hang a spring from a ceiling and attach an object of a known mass to the free end and then measure the displacement. So displacement is what delta x is. Delta x is our displacement. If we attach a mass, so we're given a mass, okay, so we're given the mass and then we're given some delta x, the displacement, and then we're asked to find K. So let's do that. Okay, so we just have, in this problem, we have a spring, there's nothing attached, and then we attach a mass to the spring, and we displace that spring by a little bit here. So this would be like our delta x. Note that it can also be vertical. It's just generally displacement, okay? That's what it represents. Okay, so our sum of forces in the y, let's look at what they might be here. Well, actually, let me draw my free body diagram first, right? Okay, so I have this mass here, okay? I know that this was my equilibrium point for my hanging spring, right? That's my spring while it's at rest. And I add a mass, and so my spring force is going to be pointing up, right? Because I've created tension in that spring, the force is trying to pull back, and then my weight is going to be pointing down, mass times gravity. Okay, so sum of forces in the y is equal to Fs minus mg, which is equal to may, right? Sum of forces is always equal to ma. So no acceleration in this case, right? Because it's just hanging in place, okay? We're not moving, we're just trying to look for it at rest, okay? The force balance at rest. Okay, so Fs is equal to mg if I just rearrange with my algebra, and then k, delta x is going to be equal to mg. K will be equal to mg over delta x. And then if we plug in the values that we are given here, 2 kilograms, 9.81 meters per second squared for gravity, because we have our delta x in meters, 0.4 meters, we're going to get a k equal to 50 Newton meters. Okay, so that tells us how many newtons per meter of force that spring is capable of producing. So for every meter you stretch or compress it, that's how much force that spring is able to exert. Okay? Cool. So let's move on to the next example.